Hi everyone, so this is going to be the last video where we have a lesson on rational functions. The next video I'll do a couple of examples for you, but this is the last video where we introduce new concepts surrounding rational functions. These concepts are ones that you'll encounter a little bit less rarely in this class, but they're still really important. And those concepts are slant asymptotes and holes in the graph. I'm going to illustrate both of these concepts using examples, and for the first example, we're looking at the function f of x equals x squared minus x minus 2 over x squared plus x. So you'll remember that in the previous video, I told you that whenever you meet a rational function, if it's easy, factor the numerator and factor the denominator. Even if it's not easy, you should try, but definitely if it's easy, you should do it right away. And what you'll notice is that on top, we have x plus 1 times x minus 2, and on the bottom, you have x times x plus 1. Oh, look at that. We have a matching factor in the numerator and the denominator. So you might be tempted right away to cross those out and pretend you never saw them, but I do want to say before we do that, that this function is not defined at -1. For example, I encourage you to do this if you plugged -1 in for x. So you would have, -1 plus 1 times -1 minus 2 over -1 times -1 plus 1, and you tried punching that into a calculator, you would get an error. So f of -1 is undefined. -1 is not in the domain of this function. All of this is true. But the fact that you have these matching factors means that there is something different going on here. So you'll notice that as I was talking, I went ahead and crossed out the x plus 1s, and we said that, well, it looks like this function is the same as x minus 2 over x. Well, is it really though? Right? And as it turns out, the answer is yes, except when x is -1. X minus 2 over x is happy as can be at -1. If you plug -1 in for x here, you would get -1 minus 2, which is -3 over -1. So -3 divided by -1 is 3. This is perfectly defined when x is -1. But our original function isn't. So what that means is that when we go to graph this function, its graph is identical to the graph of our original function f, except there's an empty hole when x is -1. So here we have, and I'm going to write that, this graph has a hole in the graph when x is -1. I'm going to go really quickly through the rest of it. So the asymptotes here, right? So now we've just shifted our attention to x minus 2 over x. We have a vertical asymptote at 0, which is where the denominator would be 0. For the horizontal asymptote, notice that the degree of both the numerator and the denominator is 1. So the horizontal asymptote will happen at the ratio of the leading coefficient, which they're both 1. So our horizontal asymptote is y equals 1. For our intercepts, so x-intercept, remember that's where y would be 0. So we would need this whole quotient to be 0, and that would happen when the numerator is 0. So we have an intercept at the point 2, 0. We don't have a y-intercept to speak of because we have a vertical asymptote at x equals 0. That's the y-axis, so no y-intercept. And then this part I'll leave you to explore on your own, but it will also never cross its horizontal asymptote. If you set x minus 2 over x equal to 1 and try to solve it, you'll see it doesn't have any solutions. So in fact, it looks like we only have one intercept to speak of. Okay, sign chart. So remember, our critical numbers come from two places. We have our intercepts and we have our asymptotes. Okay, so here we go. We have a vertical asymptote at 0 and the intercept at 2. Okay. And then we can't test 0 this time because it's one of our critical numbers. So let's test 1. It doesn't really matter what we test since 0 is off the table. And you can see when we plug 1 in for x in our function, the numerator is negative, the denominator is positive, and the quotient is negative. So since 1 lives between 0 and 2, we put a minus here, and then the sign switches around both. Okay, so there's our sign chart. Now let's sketch the graph. So I'll make a fairly small graph here. Okay, and as usual, I'm going to start by denoting the asymptote that is not already one of the axes, and that's the line y equals to 1. Okay, now I'll label my intercept, so there's only one of them. It's the point 2, 0. Okay, and now here we go. So everywhere to the left of 0, my function is positive, so the graph is above the y-axis, above the x-axis. But don't forget, I've got my asymptote to contend with here and here. So that tells me that the graph has to look like this. For my, for the other piece, between 0 and 2, the function is negative. Okay, but I do have that asymptote there to worry about. And then from 2 onward, the function is positive, but I have my my horizontal asymptote, so the graph looks something like this. Okay? Now, we forgot our hole in the graph. So you can see at -1, okay, at -1, this function would normally pass through the point -1, 3. That's this point here. So we put a hole there, and then we continue on. Okay, so I'm just going to sort of point that out to you. We have a hole in the graph. And it just happens at the point where this graph would have had an x-coordinate of -1. Okay, so that's what it looks like to have a hole in the graph. Now, let's look at the second example. So the second example, you'll notice the numerator doesn't factor. X squared minus 5x plus 1 doesn't factor nicely. And then we have x plus 2 in the denominator. So at first glance, this doesn't look that kind of unusual, but there is something interesting here. So we're just going to launch right in, talking about the asymptotes. So for the asymptotes, for the vertical asymptote, we look at the denominator, right? X plus 2 is 0 when x is -2. And then for the horizontal asymptote, we would normally look at the degrees. So let's look at the degree of the numerator. Well, that's 2. The degree of the denominator is 1. So if you go back to the video where we summarized how we tell what the horizontal asymptote is, you'll see because the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. But you might remember from that video that I put a little asterisk when I said there's no horizontal asymptote. And I said this is something we'll talk about later. And here's later. In fact, here, the degree of the numerator isn't just greater than the degree of the denominator. The degree of the numerator is the degree of the denominator plus 1. And what this means is that while I do not have a horizontal asymptote, I do have a type of asymptote, and it's called a slant asymptote. What I'm going to do to see the slant asymptote, I'm going to write this function in quotient remainder form. So this is something that, you know, in varying degrees of comfort, you all have practiced in the polynomial unit. And while we could use synthetic division here, right, because we're dividing by x plus 2, since the denominator isn't always going to lend itself to synthetic division, I'm going to go ahead and use long division here. So I have x squared minus 5x plus 1, and I'm dividing it by x plus 2. Good old-fashioned long division, right? So we're always looking at just the first terms. X would need to be multiplied by x to make x squared. We distribute. And then, of course, don't forget that in long division, we are subtracting. So we have x squared minus 5x minus x squared minus 2x. So the x squareds cancel, which leaves us with negative 7x. Then we bring down the 1. Okay. So now same thing, looking at the first two terms, x and negative 7x. X would need to be multiplied by negative 7. So we have negative 7x minus 14. Once again, don't forget, we are subtracting, okay? And then with the subtraction, the negative 7x's cancel, and we have negative 14 being subtracted, so it'll actually turn into a sum. And so our remainder here is 15. There's nothing left to bring down. So this is our remainder, and this is our quotient. So if we were to write this in quotient remainder form, we would say that f of x is equal to x minus 7 plus 15 over x plus 2. And this right here is our slant asymptote. Now, we could talk about why we know that's our slant asymptote separately, and if you're curious about that, then just pop your head into office hours and we can discuss it. But anytime you have this phenomenon that the degree of the numerator is 1 greater than the degree of the denominator, we can say, oh, there's a slant asymptote here, and we will see it by writing in quotient remainder form because it will be the quotient. Okay, so let's really quickly sketch this graph. I'm not even going to look at intercepts too carefully. This is going to be a really, really quick graph. I just want to get you a sense of what the slant asymptote looks like. So, something like this. Right, so just a really small little graph to give us a sense of what we're looking at here. So first things first, let's draw in our asymptotes. So x equals negative 2 is there. okay? And then for the slant asymptote, you'll have, so you're graphing the line y equals x minus 7. So here is -7. Did I count that correctly? 1, 2, 3, 4, 5, 6, 7. Yes. And then, I don't know, when x is 3, it's down to -4. So this is your slant asymptote. You actually have to graph the line y equals x minus 7. So it's like a little baby lesson in sketching lines, and then you would go from there. So I will give you we will look at an example more thoroughly in the next lesson. Because I've sort of run out of room here, I'm not going to do the graph really neatly here. I just wanted to show you that that's how you would plot it. So you have your slant asymptote here, y equals x minus 7, your vertical asymptote here, and the graph will look something like this. It will look something like that, and then the other piece will be down below where you can't see it. So stay tuned for the next video, in which I will more thoroughly talk through an example of a function with a slant asymptote. See you soon. Bye.